All right, now we're going to combine angles with friction. So we have a man pulling a 20-kilogram box at constant speed across a floor. He applies a 20 Newton force at an angle of 30 degrees, and we want to calculate the normal force, the friction force, and the coefficient of friction. So for every single one of these problems, let's actually start with the free body diagram. So I'm going to have this tension force. I'm going to have the normal force. I'm going to have the weight of the box. And I'm going to have the friction force right here. Now, I know that this angle here is 30 degrees. And so what I'm going to do is I'm going to go ahead and actually redraw this free body diagram in terms of the vector components. And whenever we have forces at angles, we do exactly what we did with velocities at angles and every other quantity that we deal with at an angle. We actually have to split it into its x and y components using vectors. So I'll redraw this as Fn. This is F, force of friction here. And you know what? I'll actually write it. There we go. We have the gravity force. And now this tension is going to get split into two pieces. The first piece, we're going to have Tx, and the other piece is going to be Ty. And if we use our vector notation, this is going to be, you know what, I just want to make it a little bit thinner so we can read it. That's going to be T times the sine of 30. And this is going to be T times the cosine of 30 right there. Okay, we're moving at constant speed. So what this tells me is that our forces are balanced. And while I'm here, let me just do one other thing. Since this is the mass, we can get Fg as m times g. And so that's going to be 20 times 10, which is going to be 200 newtons worth of force. All right, next thing. Let's go ahead and set up our vertical and our horizontal forces. So for part A, we want the normal force. So let's go ahead and actually set that up right now. So I'm going to have T sine of 30 plus Fn going up minus Fg equals 0. Let's go ahead and actually put in our numbers. So we're going to have 200, and the sine of 30, by the way, is 0.5 when we calculate that. So that'll be 200 times 0.5 plus our unknown normal force minus Fg, which is 200, and that's going to equal 0. So we're going to end up getting 100 plus Fn minus 200 equals 0. And finally, when we simplify, the answer to part A is that Fn is going to equal 100 newtons. All right. Now, let's get the horizontal friction force opposing the motion of the box. We'll get the size of that. So horizontally, we know that Tx minus the force of friction, they balance because we're moving at constant velocity. So that means T cosine of 30 minus the force of friction equals 0. So that's going to be 200 times 0.87 when I take the cosine of 30 and round it, minus the force of friction equals 0. So our friction force is going to end up being about 174 newtons. Okay. You might get 173 if you round. I'm just kind of kind of calculating it out here, like just there's the friction force with rounding. So for part C, the coefficient of kinetic friction. Well, we know friction, kinetic, is going to equal mu kinetic times the normal force. So I'm going to end up getting 174 equals mu kinetic times 100. So it actually looks like here mu kinetic is going to end up being, we'll take 100 divided by 174. And let me just do that in the calculator real quick. So 100 divided by 174. Let me make sure I have that right. No, it's 174 divided by 100. Sorry about that. So I'm going to end up getting 1.74 as my coefficient of friction. All right, so that is page 3.